double bond of the dienophile, that means this one here, are now different because the chiral centers, in these two faces of these two faces of the double bond of the dienophiles are now different because the chiral centers, they are the distereotopic, and the diene can be distinguished between them if we now do the Diels-Alder reaction in the presence of the Lewis acids. Here this is the Lewis acids. The aluminium chelates the oxygen here, oxygen atoms of the dienophile, to form the rigid and reactive structure here shown below. Here this is the green part of the molecule, that means this is a chiral auxiliaries. And here this is a Lewis acids, okay, and here there is a chelation complex between the oxygen and the aluminium, and here the isopropyl groups is shielded. Here this is most important case, that means this isopropyl groups is held in such a way that the steric bulk prevents the diene attacking that phase of the prochiral alkene. Therefore the diene has no choice but attack from above, and only one possible diastereomer product is formed. Here the isopropyl groups are present, therefore the attack of cyclopentadiene, it must from the top face. That means here the bottom face of the dienophile is shielded from the attack, okay. Therefore due to having some steric hindrance, therefore attack does not take place from the bottom face, is attack from the top face. And here we get the only one diastereomer is formed enantiomerically pure. Here we get the only one diastereomer is formed, and it is enantiomerically pure because here in starting material, that means the green part of the molecule, that means this chiral auxiliary, here the isopropyl groups are present, therefore having some steric hindrance, therefore the addition of diene, that means cyclopentadiene, it takes place from the top face, it having only one choice, therefore we get the only one diastereomer formed, and it is enantiomerically pure. And the last steps to completion of the reaction, remove the chiral auxiliary, and this chiral auxiliary is removed by treating with the nucleophiles. Here this is a nucleophiles, I mentioned here, we can write here ROBN, LIOBN, sorry, this RO minus, it will be attacked, that means act as a nucleophile, this will be attacked, and here departure of this chiral auxiliary, and we get the single enantiomers, and this chiral auxiliary is recovered and can be recyclized for the next reaction. This is the specialty of the chiral auxiliary, that means it can be easily attached and easily removed, and there is no wastage of any other byproduct. Now the next, the norepinephrine is used as a chiral auxiliary. Friends, the naturally occurring cheap compound, that is norepinephrine, is used as a chiral auxiliary, and it is easily attached and easily removed. Here this is the structure of norepinephrine. Here there is simple reaction, and we get the chiral auxiliary. Here again first step, here the hydroxyl getting this lone pair, it will attack on this ketone and departure of this one OET group. In now then second step, the NH2 will be attack on this ketone and departure of second OET molecule, and here we get the one intermediate, or we call it as the chiral auxiliaries, okay. Now on treatment with the sodium hydride, in sodium hydride it will abstract the, the sodium role of sodium hydride base, it will abstract the more acidic proton from this direction, okay. Here now then the next step, it will be attack on this and departure of this chlorine, and here we get the one intermediate steps. Now the most important steps is here, the cyclopentadiene is must attack from the bottom face, and here the top face of the dinophile shielded from the attack due to this chelation complex. Due to this chelation complex, and these two groups are above the plane. Therefore, the top face of the dinophile shielded from the attack. That's why the cyclopentadiene is must attack from the bottom face. This is most important, friends. Okay, why the cyclopentadiene is attack from the bottom face? Because here from the top face of the dinophile is shielded from the attack. That means here there is chelation complex first case. Now the most important is there is presence of these two groups. That means this methyl and the pH groups are above. Therefore the cyclopentadiene is attacked from the bottom face, and here we get this one intermediate. Now then next step, there is a removal of these chiral auxiliaries. Opposite enantiomer formed with this chiral auxiliary, and here we get the final product. Here the two substituents, this is most important, I have repeated, the two substituents of the chiral auxiliary lie on the top face of the dinophiles, and they force to the cyclopentadiene, and this time to attack the bottom face. Now when the chiral auxiliary is cleaved from the product, the opposite enantiomer is formed. Here we get the opposite enantiomer is formed. This is the simple way to remember this, the actual mechanism of chiral auxiliary. So in this way the norepinephrine is used as a chiral auxiliary. In this reaction, this is the most important case. That means the reactivity, how the cyclopentadiene is react. Here the cyclopentadiene is react from the bottom face because there is presence of these two substituents is on the top face. Therefore they shield the position. From the top face it having some steric hindrance. Therefore the cyclopentadiene is attacked from the bottom face, and we get the opposite enantiomer formed with these auxiliaries. Now the next, the chiral auxiliary can also be used in a different types of reaction, that is alkylation of enolate. The chiral auxiliary in alkylation of enolates. Here the enolizable carboxylic acids and their derivatives, here treatment with the base, that is LDA, usually LDA at low temperature, and to produce the here a trans enolate. To produce the trans enolate, the bulky auxiliary means that only cis enolate is formed and the trans enolates to hindered. That means here this is simple case. Here NaH will abstract this more acidic proton. Now then this will be attack on this and departure of this chlorine. Here we get the intermediate. Now then LDA, it is sterically hindered. If we abstract the more acidic proton here, and we get the there is formations of enolate. We have to remember that each and every step, if we use the LDA, there is formations of the enolate. Definitely there is formation of the enolate. Here we get the cis enolate. And this is the trans enolate. These two hindered. Why? Because this is isopropyl groups and this methyl group, it having some steric hindrance. Therefore trans enolates is too hindered as compared to the cis enolates. Now here the electrophile attack from the top face of the enolates, because at the bottom face it is shielded by the isopropyl groups. Therefore addition of the electrophile is take place from the top face. Now the coordination of lithium ion to the other carbonyl oxygen makes the whole structure is rigid. That means due to this it is nothing but the coordination, and due to this coordination with the lithium and oxygen, the whole structure it is rigid and fixing the isopropyl groups around the back to the molecule, where it can provide the maximum hindrance to attack the wrong face of the enolate. Now the electrophiles have the little choice but attack the enolate from the front, and this table shows the ratio of diastereomers The diastereomeric ratio is abbreviated as DR, produced for the selection of alkylating agent. That means here the addition of electrophile is from the top face of the enolate, okay, because the bottom face that is shielded of isopropyl groups. Therefore here if you add this alkyl halide is become a front side, okay. Now this is the major diastereomer and this is the minor diastereomers, and if you see these tables, the diastereomeric will if you use Rx, that means here benzyl bromides is diastereomeric ratio is 99.9. Now then alkyl bromide 98.2, and for ethyl iodide it is 94.6. Okay. Now in alkylation of enolates, this most important is that the addition of electrophile. Addition of electrophile. First step, when you use LDA, there is formations of the enolate. Here, in this reaction, cis enolate is more preferable as compared to the trans enolate, because in case of trans enolate, it is having some steric hindrance, therefore cis enolate is more preferable. Now, the electrophile attack from the top face of the enolate, not from the bottom face, because in bottom face it having some steric hindrance, therefore addition of incoming electrophile is become a front side, and we get a major diastereomer. Now then the enantiomeric excess. The definitions of the enantiomeric excess, that means the ratio, it is a ratio actually. The enantiomeric excess or the EE is defined as the excess of one enantiomer over the other, and it is expressed as percentage of the whole. So the 94:6, the mixture of enantiomer, consists of one enantiomer in 88% excess over the other, and we call it as the enantiomerically enriched mixture with 88% E. In here the simple reaction, this is the 94:6 mixture of diastereomers, and here to remove the chiral auxiliary by reduction by using lithium aluminum hydride, we get the 94:6 the mixture of diastereomer, and here the enantiomeric excess is 88%, and we know the formula to calculate the enantiomeric excess. The enantiomeric excess is calculated by using simple formula, that is enantiomeric excess EE is equal to cis minus trans divided by cis plus trans into 100. Okay, this is about the enantiomeric excess. And the good chiral auxiliary is needed, and it is one derived from the norepinephrine, and the reaction of this enolate with the allyl iodide gives 98:2, the mixture of diastereomer. Here this is simple reactions. Here first this NaHMTS, this act as a base, okay, this act as the base, it form the here enolate, and this will be attack on this allyl iodide, and here we get the one intermediate. In next step there is the removal of these chiral auxiliaries, okay. We know the when you use the lithium aluminum hydride, at that time there is a removal of these chiral auxiliaries here, and simultaneously there is a reduction of this here this functionality, that means C double bond and it will be converted into alcohol here. And next step there is protection of this alcohol by using the tertiary butyl dimethylphenyl chloride, and we know that the tertiary butyl dimethylphenyl chloride, it is the best for the protection of the alcohol. Therefore here the simultaneous, this is a simultaneous mechanism, that means the here removal of chiral auxiliaries, and again there is reduction, we get the alcohol, and here protection, and we get the 99% EE, that means the fragments here of X206. Now then the here and we get the recovered auxiliaries. This is about the simple mechanism of chiral auxiliaries. Now this is most important. So how to remove the chiral auxiliary? This is a one big bonus of using chiral auxiliaries. it is much easier to purify the diastereomers than the enantiomers, and the chiral auxiliaries control the reaction if the necessary produces the diastereomer product here. uh, both the both these examples of auxiliary control the alkylation, make use of lithium aluminum hydrides. Here there is simple removal of these chiral auxiliaries, and the simultaneous reduction we get the alcohol. Here removing the chiral auxiliaries, that means there is a reduction to the alcohol in the steps, and which removes the chiral auxiliaries. And you saw the attack with alkoxide above, and several other alternative methods are possible as well as summarized below. Here the debal, okay, again for debal, again it is used for to remove the chiral auxiliaries. Here we get the aldehyde, and we know that the when amide on treatment with the debal we get the aldehyde. And next here LiOH in presence of H2O2, then protonation, the hydroperoxide is a more nucleophilic and less basic than OH minus. And here we get the carboxylic acids. And now then, while converting the product, that is Weinberg amide. Here it is simple, again it is the Weinberg amide. It is again used for to remove the chiral auxiliaries. In next step there is on treatment with the Grignard reagents, and we get the finally we get the given product, that means the ketone. Okay, that means this is a simple way to remove the chiral after completion of the reaction, to remove the chiral auxiliaries by using these various types of these reagents. Here the chiral auxiliaries derived from the L-phenylalanine. These are various ways of removing the chiral auxiliaries, and it is illustrated ways in which the possible to make virtue of the one of their a big disadvantages. The chiral auxiliary must first be attached to the compound under construction, and after they done their job they must be the removed. That means after completion of this reaction they can be easily removed, and the best chiral auxiliary can be recyclized. But even then there is still at least two unproductive steps in the synthesis. Here again this is the base, it will abstract this proton, okay, and here we get the this is carbanion or enolate, and this will be attack, and here departure of this bromine, and we get one intermediate. Now then next LiOH H2O2 and H3O plus. We know the role of this reagent, that means just removal of this chiral auxiliary, and we get the product. Okay, this is a second part of chiral auxiliaries. Different types of reactions are involved. This is the chiral auxiliaries. Here the chiral auxiliary on treatment with the NaBH4 or lithium aluminum hydride is a reduction, and we get here alcohol. Now then ammonolysis, we get the amide. Now then hydrazinolysis, we get the hydrazides. Now then alkalolysis, we get the ester. Now then hydrolysis, we get the carboxylic acids. Now then on treatment with the debal, here remove the chiral auxiliary and we get the aldehyde. That means these are the simple reaction to remove the chiral auxiliary, and we get the final product. Now tricks to remember the actual chiral auxiliaries. Friends, the chiral auxiliary here, this is a prochiral substrate, and this prochiral substrate is attached with the chiral auxiliary. I have mentioned here H, here Y, C, A. C, that means the chiral auxiliary. In first step, the chiral auxiliary is attached to the